Today we're going to talk about the kinetic theory of matter, which is a way of explaining why these gas laws should work. We know they work because they're laws. They've been experimentally verified over and over again. So what's the explanation? Why should it work? Well, it's closely related to our basic scientific idea that everything is made up of tiny particles that are moving around all the time. First, we'll start out with a quiz skin or two. Stop the video, read through this, and give this a try, and I'll give you an answer in a bit. Helium weather balloon, supposed to have a volume of 100 cubic meters at 740 torrs, 22 degrees C. Can you fill this balloon up with the helium that's in a cylinder that holds 130 pounds of helium? Well, I want to know how many moles of helium are in the cylinder, and then I want to know how many moles of helium are going to fit in the balloon, and then I'll compare them to get my answer. So I'll attack the cylinder first. I know that there are 130 pounds of helium in this cylinder. I know that there are 2.20 pounds in every kilogram. If you didn't know that, hopefully you looked it up. That tells me how many kilograms are in that cylinder. But I want grams so I can convert this to moles, so I'll use the fact that there are 1,000 grams in 1 kilogram to convert. And that tells me how many grams are in there. And then it's helium, so 4.003 grams for every mole. And this is going to tell me how many moles of helium are in the cylinder. When I work it out to two significant figures, I find out that there are 15,000 moles of helium in that cylinder. So, how many moles are going to fit in the balloon? Well, number of moles in any space is equal to PV divided by RT for gases. So, I'll put my pressure in. Well, the pressure is given to me in torr, which I have to convert. So 740 torr at 760 torrs per atmosphere gives me 0.973 atmospheres. That's what I put in for pressure. Volume. I have to have this in liters, but I don't. Right now I have it in cubic meters. How can I convert? Well, one thing that might help me is recognizing this. If I have a cubic meter, 1 cubic meter, this is 100 centimeters by 100 centimeters by 100 centimeters. So that's 100 cubic centimeters. So let's start a conversion here. 100 cubic meters, and now I know that 1 cubic meter has 100 cubic centimeters. That gets me how many cubic centimeters are in this balloon. However, I want this in liters, and a milliliter and a cubic centimeter are the same thing, so that means 1,000 cubic centimeters in 1 liter, and that'll convert me into liters. When I do this, I find that I get 1.00, because this had a decimal point after it, times 10 to the 5th liters. That's my volume. So I'm going to put this in my ideal gas law. 1.00 times 10 to the 5th liters. R is 0.0821 liter atmospheres per mole Kelvin. And my temperature, well, it says it's 22 degrees C, and that's 295 in kelvins. So when I work this out, it'll be moles. I should have 3 significant figures, and it comes out to 4,010 moles. So I need 4,010 moles to fill the balloon up. Inside the cylinder, I have 15,000 moles of helium, and so no problem. The cylinder can easily fill this up. Here's a related quiz skin. If that 130-pound helium cylinder in the last problem has a volume of 219 cubic feet, what's the pressure of the helium in the cylinder at 22 degrees C? Well, to find pressure, we can use the ideal gas law, which will tell us that P is nRT divided by V. We calculated that there were 15,000 moles in that cylinder. R, we already know what that is. It's 0.0821 liter atmospheres per mole Kelvin. And the temperature was 22 degrees C, which is 295 kelvins. volume of the cylinder, we don't have that in liters, which we have to have, so we're going to have to convert. It was 219 cubic feet. Now, we want that to end up in liters. I know that every 1 foot has 12 inches. So using the logic from the last problem, I should be able to say that 1 cubic foot has 12 cubic inches. You can draw yourself a picture and work that out if you're not comfortable with it, but it's going to work. And I know that there are 2.54 centimeters in 1 inch, so a cubic inch should be 2.54 cubic centimeters. And that will get me to cubic centimeters, which are the same thing as milliliters, and then there's 1,000 of those in 1 liter. So I've converted if I just do my arithmetic now. And this comes out to 6.20 times 10 to the third liters. So that's the volume that'll go in here. And my pressure will now come out in atmospheres, because the liters will cancel, the moles will cancel, the kelvins will cancel, leaving me only a unit of atmospheres. I'll have 2 significant figures in my answer, and it's 59 atmospheres. This problem's a little bit tricky. It's going to require a little bit of creative thinking to solve this. But I'll give you a hint. It has to do with Graham's law of diffusion. This isn't actually diffusion. This is called diffusion, but the law works pretty well for diffusion as well. So you have samples of ammonia and hydrochloric acid. They have different molar masses. That will be a hint. They're introduced into opposite ends of a 4-foot long tube. So here's the setup. I have a tube. The tube is 4 feet long. Into one end, I put some ammonia. Into the other end, I'm going to put some HCl. When the gases meet, wherever that is inside this tube, you're going to get this ring of NH4Cl as the acid-base neutralization forms this solid powder in the air. Question is, how far from the NH3 end will the ring form? So I want to know how far from here to where the ring forms. Give this a try. Graham's law of diffusion is going to be part of the solution, but how you use that, well, that's up to your creativity. So here's my 4-foot tube. And I'm going to say this is the ammonia end and this is the HCl end. They're going to meet somewhere in the middle. Well, let's look at the molar masses of these 2 compounds. First of all, ammonia, if I look up its molar mass, it's 17.031 grams per mole. And if I do the same thing for hydrochloric acid, I find out that it weighs quite a bit more, 36.461 grams per mole. So the one that's lightest is going to effuse the fastest. So somewhere towards the HCl end, I'm going to find out where that ring is. So let's call this distance NH3. And let's call this distance here 4 feet minus distance NH3, just so that we have only one variable. Now, if you've had 7th grade math or physics, you know that distance is equal to rate times time. And these things are going to be effusing for the same exact amount of time. So I have a law about rates, and it says this: the rate of one of my gases, like NH3 for example, divided by the rate of a second gas, like HCl for example, is equal to the square root of the molar mass of the bottom gas, HCl, over the molar mass of the top gas, which would be the NH3. But since distance is rate times time, watch this. If I just multiply time on top and bottom, it cancels out, right? Because it's the same time. They're both going to be in the tube for the same amount of time. So rate times time is distance, so I could replace these. I could say distance NH3 over the distance of HCl, which is 4.0 feet minus the distance NH3. We established that on our drawing. That's equal to this same ratio. Molar mass of HCl, which is 36.461, divided by the molar mass of NH3, which was 17.031 grams per mole. So if I work out my math here, distance NH3 divided by 4.0 feet minus distance NH3 equals 1.4632. So it's just a simple algebra thing from here. distance NH3 is equal to 1.4632 times 4 feet minus distance NH3, which becomes 5.9 feet minus 1.4632 distance NH3. So that means 2.4632 times distance NH3, if I add 1.4632 to both sides, is equal to 5.9 feet. So if I solve for distance NH3, here's what I find. It's equal to 2.4. Now we're going to spend some time talking about the kinetic theory of gases, or the kinetic theory of matter. And this might seem really theoretical and abstract to you. I mean, well, it's a theory. But this is actually, I think, a really fundamental point to get in your scientific education. I think if you don't ever learn anything else in a science class, it's probably the most important thing that you can learn, is that everything is made up of little teeny tiny particles that are constantly moving. We call them atoms or molecules or ions, but why do we believe that they're there? There are a lot of good reasons. And the gas laws give us strong evidence that everything is made up of small particles, tiny particles, lots of them, that are in constant random motion. That's the heart of the kinetic theory of matter. So that's the first postulate. A lot of particles in constant random motion. Another postulate of the kinetic theory is that the volume of the particles themselves is so small compared with the space that they're in that you can ignore them. There's a phrase that's used to describe this idea, and that's called point mass. They're considered to be tiny points of non-existent volume that have mass. Of course, that's not true. It's theoretical, but it gives us a pretty good approximation, a model to work off of. Another postulate of the theory is that the particles don't interact with each other. When the particles hit one another, they don't stick, they're not attracted to each other, they bounce off. So that means that they have perfectly elastic collisions when they hit each other. They bounce in with a certain amount of energy and they carry away the same amount of energy. And another consequence is that the particles move in straight lines between collisions. So if a particle bounces off the wall of a container and starts moving past another particle, it doesn't get veered towards that particle or away from that particle. It just goes in a straight line until it hits the next object, another particle or another wall of a container. So the particles move in straight lines and they collide with no loss of energy. Neither of those things is true, but it's a model that's close enough to reality that it works pretty well. One of the consequences of the kinetic theory of gases is that you should be able to figure out what's the velocity of a gas particle, theoretically. And so we have an equation for this. I've prepared a separate video that you can watch if you're interested in knowing the details of this, which are pretty interesting if you're into how math explains science. But it's optional. You don't have to look at it if you don't want to. But this is the bottom line. This is called the root mean square velocity. We use U for velocity here. Root mean square is sort of a way of saying average, and it takes out the fact that it's moving in all different directions. So if I have a particle that's going this way and another particle that's going this way, I don't want them to cancel each other out, because then my average becomes 0. So the root mean square takes the square root of the squares averaged, and that's what we're talking about here. So basically it's how fast is every particle moving on average inside of a collection of gas. And it's given by this equation. 3,000 times R times T divided by molar mass. T is temperature, R is universal gas constant, and then you all know what molar mass is. Now, we're going to apply this, and we're going to find out that the R that we have needs to be modified a little bit. Same number, same constant, but we're going to have to express it in a different unit. So let's look at this problem here. It says calculate the average speed of a molecule of oxygen at STP. Okay, root mean square velocity is equal to the square root of 3,000 times R, which is 0.0821, liter atmospheres per mole Kelvin, times the temperature, which is 273 kelvins because it's at STP. And then this is going to be divided by the molar mass. Well, oxygen exists as O2 here, so we have to use 31.998 grams per mole to make this work out. Now, before I calculate this, I want to take a look at the units. Here what I've got is, under the square root sign for units, I have liters times atmospheres times kelvins divided by moles times kelvins divided by grams divided by moles, which is equal to the square root of liters times atmospheres times kelvins divided by moles times kelvins times moles over grams. Well, that's equal to the square root of, if I cancel things out like kelvins and moles, liter atmospheres per gram. If I take the square root of liter atmospheres per gram, I don't have anything that sounds like a velocity. Velocity would be something like meters per second or miles per hour. It would be a unit of distance over a unit of time. So that tells me that I can't use 0.0821. What I'm going to have to use here is a different version of the universal gas constant. It's the same constant, but it's just evaluated with different units. This is the other version of R. R is 8.314 joules per mole per Kelvin. And it's also equal to, as we've been using, 0.0821 liter atmospheres per mole Kelvin. Here, to make the units work out, we're going to have to use this one. Let's see how the units work out down here. If I have joules per mole Kelvin times kelvins divided by grams per mole, and then I start to break down joules a little bit. A joule is a Newton meter. A joule is a Newton times a meter. So that means I have the square root of newtons times meters times kelvins divided by moles times kelvins divided by grams per mole. And the kelvins are going to drop out here, and the moles are going to drop out here. So this gives me newtons times meters divided by grams. But a newton is a kilogram meter per second squared. We saw that in an earlier video. So let me break this down even more. A newton is a kilogram meter per second squared. But the newton meter means I have kilogram meters squared per second squared, and that's all divided by grams. Well, look at this. I have square meters on the top, and I have square seconds on the bottom. If I could take the square root of just that, I'd have meters per second. But the kilograms and the grams won't cancel. But remember, I'm multiplying this by 3,000. And the reason I'm multiplying by 3,000 is for this reason. It's just to make the units work out. 1,000 times the number of kilograms is the number of grams. So by moving the 1,000 part of the 3,000 in here, I've got this for units. I've got grams times meters squared divided by second squared times grams. And that's all under the square root sign. So when the grams cancel out, I come up with meters per second. So now that I know the units work out, I'm going to sort of ignore units, and I'm going to start over again and do this calculation. But this time I'm going to use the correct value of R. All right, so root mean square velocity is equal to the square root of 3,000 times R, but now I'm going to use 8.314 joules per mole Kelvin times the temperature, 273 kelvins, divided by the molar mass of oxygen, 31.998 grams per mole. And I now know that my units are going to come out to meters per second when I do this calculation. And it comes out to 461 meters per second. 461 meters per second is over 1,000 miles an hour. So these little particles are really flying around pretty fast. And that's at standard temperature, which is freezing. If it gets hotter, they're moving even faster.